Hi, everyone. I'm glad to present our work on multiple descent of minimum norm interpolants and restricted lower isometry of kernels. This is Zhai from MIT. This is joint work with Tengyuan Liang from Chicago Booth and Rakhlin from MIT. So I will first introduce our motivation, which is minimum norm interpolants, and then I will share our results, which is a multi-descent behavior of risk upper bounds. And then I will talk about application to wide neural networks. And I will also share our main proof techniques, which is restricted lower isometry of kernels and small ball property. So in many cases, our model class is complex enough to interplay the training data. So in fact, as you can see in the figure, many models behave the same on training data. So what model we choose is going to be dependent on the specific algorithm we use. The principle is among the models that interpolate, algorithm often favor a certain form of minimalism. So this can be seen in popular used methods like overprime-tried linear model, matrix factorization, kernel machines, support vector machines, and two-layer ReLU networks. Okay. So these minimalism typically mirror in certain form of a norm. This is norm in a function space, something. So this motivates the study of minimum norm interpolants. So mathematically speaking, look like this equation. Okay, so here that's about motivation. So what we want to study, risk curve. Yeah, risk curve is a very important object to study. So classically, people shown a U-shaped curve for risk, plotted against a bandwidth. So this is mainly because of the bias variance trade-off. Now, recently we have discovered, people have discovered a multi-descent curve for risk, as in two papers in 2018 and 2019. Now the question is, our question is, what the shape of the risk curve look like if we plot it against dimensionality? So here we have a model of the high dimensionality like this. So D is roughly proportional to n to the alpha's power. And the feature covariance matrix is IID isotropic. So we also consider nonlinear kernel regression model. So here, nonlinear kernel regression model is key to our results. More specifically, we have this generation process of our data. The input, the design is basically every IID. The each entry is IID. So and we also put a weak moment condition on the distribution so that it doesn't do crazy things. And we also require the kernel to be in a product kernel. So H is Taylor expandable, and also the function H is Taylor expandable with positive Taylor coefficients. So and we also require certain smoothness assumption on the target function. So it can be generated from integration that looks like this. So here, one thing to mention is that our requirement that the kernel is Taylor expansible with positive Taylor coefficient is not a very strong requirement. It can be somehow inferred from the fact that this is indeed a kernel, a positive one. So for all dimensions. So it's kind of a natural assumption. So yeah, so we having these settings, we study high dimensionality, and we want to know the risk curve for minimum RKHS norm interpolants. So here is our theoretical results. So for any integer alpha larger or equal than 1, we consider d proportional to n to the alpha power, where alpha is between this interval, 1 over alpha plus 1 and 1 over alpha. Then with high probability on the design, we have the risk or the expected value of the risk being upper bounded by n to the minus fifth power. So here beta is related to alpha in this way. So it's a multi-descent behavior. So this is kind of surprising because people normally think that the more data we have, the better our result will be. But the thing is, here we have dimensionality increase as the number of data increase. So yeah, so it's kind of this interplay between the high dimensionality and more data that creates somehow this strange behavior. So we can see that the valley on the rate curve occurs at d roughly to this power of n. And we can also see this trend that towards our franchise regime, the good rate at the bottom of the valley is better. And empirically, we also obtain similar results, although this is just a theoretical upper bounds. So empirically, we also have this multi-descent behavior, as you can see in this plot. Making comparison look like this. So on the left is the theoretical result, on the right is the empirical result. These are all plotted as logarithm on a log scale. So yeah, and the plot on the left, this theoretical one, is kind of the asymptotic behavior. So that's why it's so rigid. Okay, so we have many related work. Alpha equal to 1, alpha equal to 0, alpha equal to 1 W10, alpha random trivial feature. Yeah. So it's there. We believe there's definitely something going on now that there are so many papers on this. Okay, so far is for kernel methods. What about the other methods? So luckily we can directly generalize our result to wide neural networks, where NTK. So neurotypic kernel is something that can link wide neural network to kernel methods. So people have discovered that if a neural network is very wide, its behavior is going to look like a kernel regression. So yes, and the kernel corresponding to this is the neurotypic kernel. It has this form. You can see it's a you have the two norms and then a function of the cosine. So here the function is Taylor expanded as this. You can see the Taylor expansion is of all positive coefficients. And the thing is that this neurotypic kernel is not quite the same as an inner product kernel. So we have to modify our proof a little bit, but luckily the result is quite similar. So we would expect the same multi-descent behavior for very wide neural networks under our high dimensionality setting. Okay, so let me share with you what is the mean proof techniques. Okay, so first, what is the difficulty we faced? So basically, after decomposing the risk to bias and variance, we surprisingly find out that both terms can be bounded by this quantity. So it's a matrix inverse times a vector. And we compute the expectation of the norm squared. So this doesn't look, so one can directly bound it like this. So use the spectral norm. But the bad thing is that this spectral norm is too large to be useful. Our observation is that the vector doesn't necessarily lie in the direction of large eigenvalues of the matrix inverse. So it could happen that the majority of the vector lies in the direction of small eigenvalues. So the product of the matrix inverse and the vector isn't going to be too large. Okay, so how are we going to utilize this knowledge? Okay, so our solution is to filter the space so that we can show that only a small part lies in the direction of large eigenvalues. Okay, so here is going to be a lot of details. So we first decompose our kernel into an infinite sum. And we define field treated empirical kernel. So here k with alpha on the with alpha is kind of like the first alpha plus one partial sum. So these partial sums can be seen themselves as kernels, as partial kernels. So these partial kernels corresponding to space of polynomial functions of degree less than or equal to alpha. Okay. So yes, so it's like field treated kernel corresponding to field treated vector space subspaces, and we can decompose each field treated empirical kernel into a product, and we can like transpose the product so that we get a field treated sample covariance operator. So nice thing is that these two sample covariance operator and the empirical kernel have the same non-zero eigenvalues. Okay, so what we want to prove is a property called restricted lower isometry of kernel. So it's like all non-zero eigenvalues of partial k of order alpha is larger than this one. You can see that we have different bounds for different partial kernel. So this is very important. This is very important. And we have three intuitions. Like the first one, non-zero eigenvalues are the same, so we can just take care of the sample covariance kernel. And secondly, this is correct. And secondly, we suppose the features are orthogonal, we can have the theta to be and the expectation to be diagonal. But luckily, this is wrong. And lastly, maybe we can use standard concentration to show that theta is converging to something, but this is again wrong. So we have to do something here. So we have two ideas that can make the intuition correct. The first idea, we apply a Gram-Schmidt process to make the features orthogonal. Now we will have our theta under expectation to be diagonal matrix. But the price we have to take is we lost independence of features. But we have a third moment inequality. This is like a triangle condition. And with this condition, we do some very tricky calculations that we can get our work done. And the second idea is to small ball property, because we can't just have standard concentration. It's too difficult. Yes. Yeah, just roughly. So because why we can use small ball property here is mainly because what we want to prove is not the matrix close to something. We just need to show that its smallest eigenvalue is larger than something. So yeah, we can use small ball property here. Okay, so then we get this and return to multi-descent proof. Okay, so we decompose the vector into many parts, and we apply the matrix inverse to each part. And for different term, we use different bounds. So this is like a filtration of space. Like we distribute things well, so that in the end the upper bound is reasonable. Yes. Okay. So here these are the proof techniques. So the open question is now we have upper bound that looks similar to empirical result, but how to get a lower bound? Okay, this will be a future direction to work on. Okay, thank you for listening.